using a confidence interval to test hypotheses. Our approximate 95% confidence interval for the average age in the population goes from 26.9 years to 27.6 years. Suppose someone wants to test the following hypotheses. The null hypothesis says, well, the average age in the population is 30 years. The alternative hypothesis, which is the complement of the null hypothesis, says the average age in the population is not 30 years. It's less or more. How do we test this hypothesis? If you were using a 5% cutoff for the p-value, you would reject the null hypothesis. This is because 30 is not in the 95% confidence interval for the population average. At the 5% level of significance, 30 is not a plausible value for the population average. This use of confidence intervals is the result of duality between confidence interval and tests. If you are testing whether or not the population mean is a particular value like X, and you use the 5% cutoff for the p-value like 5%, then you reject the null hypothesis if X is not in your 95% confidence interval for the population mean. This can be estimated by statistical theory. In particular, in practice, it just boils down to checking whether or not the value specified in the null hypothesis lies in the confidence interval. If you were using the 1% cutoff for the p-value, you would have to check if the value specified in the null hypothesis basically lies in a 99% confidence interval for the population mean. To a rough approximation, these statements are also true for population proportions, provided the sample is large enough. While we now have a way of using confidence intervals to test a particular kind of hypothesis, you might wonder about the value of testing whether or not the average age in a population is equal to 30. Indeed, the value isn't clear, but there are some situations in which a test of this kind of hypothesis is both natural and useful. Comparing baseline and post-treatment scores. We will study this in the context of data that are a subset of information gathered in randomized controlled trial about treatments for Hodgkin's disease. Hodgkin's disease is a cancer that typically affects young people. The disease is curable, but the treatment can be very harsh. The purpose of this trial was to come up with dosage that would cure the cancer but minimize the adverse effects on the patients. The table Hodgkin's contained data on the effect that the treatment had on the lungs of 22 patients. The columns are height. You have a measure of radiation to the mantle. A measure of chemotherapy, a score of the health of the lungs at the baseline, that is at the start of the treatment. Higher scores correspond to more healthy lungs. You have the same score of the health of the lungs 15 months after the treatment? Let us take a look at our table. We're looking at the first 3 rows. You have the height, you have basically the measure of radiation, you have the measure of chemotherapy, so you have the score of the health of the lungs at baseline, and then the same score after 15 months. We're going to compare the baseline and 15-month scores. As each row corresponds to one patient, we say that the sample of baseline scores and the sample of 15-month scores are paired. They are not just 2 sets of 22 values, but 22 pairs of values, one for each patient. At a glance, you can see that the 15-month score tend to be lower than the baseline score. The sample patient's lung seem to be doing worse 15 months after the treatment. This is confirmed by the mostly positive values in the column drop, the amount by which the score dropped from the baseline to 15 months. So let us take a look at our result of the line of code here. You can basically see the difference. You have 72.8, 30.62, some negative numbers, and some large positive numbers. And our histogram is drawn on the right-hand side. The average is 28.62. So in the sample, the average drop is about 28.6. The question is, this could be the result of chance variation or not. The data are from a random sample. Could it be that in the entire population of patients, the average drop is just 0? To answer this question, we can set up 2 hypotheses. Null hypothesis, which says in the population, the average drop is 0. Alternative hypothesis says in the population, the average drop is not 0. It's either less than or more than 0. Our goal is to test the hypothesis. And we're going to use 1% cutoff for the p-value. Let us construct and approximate 99% confidence interval for the average drop in the population. We're going to define our function as usual and make sure to resample and returns the average. We're going to repeat this process 10,000 times. And we define the left and right endpoint to be 0.5 percentile and 99.5 percentile. So it captures the true population parameter. The result is a confidence interval with left endpoint 17.47 and 40.98. We're using bootstrap method. Let's take a look at our histogram. In our histogram, the yellow line shows the 99% confidence interval. The 99% confidence interval for the average drop in the population goes from about 17 to about 40. You can visualize this just right here. The interval doesn't contain 0. So we reject the null hypothesis. Please note that we have done better than simply conducting that the average drop in the population isn't 0. We have estimated how big the average drop is. That's more useful result than just saying that, hey, it's not 0. A note on accuracy. Our confidence interval is quite wide for 2 main reasons. First of all, the confidence level is 99%. The sample size is relatively small. In the next chapter, we're going to check how this sample size affects accuracy. We'll also examine how the empirical distributions of sample means often comes out the bell-shaped, even though the distribution of underlying data are not bell-shaped at all.